we're talking about we were talking about continuity, and we had a piecewise function absolute value of x minus 1, but I'm going to do x minus 2. Remember how we have to write this as a piecewise function because we don't like absolute values because they are basically piecewise functions. So this is x minus 2 when x is greater than 2. And this is negative x minus 2 when x is less than 2. Now, in the last video, I said the function changes definition at 0. I was wrong. I changed it in the video. I said it was a 1. Now, how do we know if a function changes definition? It changes definition for absolute value when it crosses over the 0. So how do we get 0 here? When we plug in 2. Everywhere else we get negative and positive, and the function changes definition. So find what makes the absolute value equal 0. That's when the function changes definition. Then do a one-sided limit, and you have to be careful where you take it from the left and right. X is greater than 2, it's from the right. X is bigger than 2, it's from the left. So less than 2, it's from the left. That's all I wanted to point out. Okay, this might be the most important topic in calculus. Here we go. We're going to talk about the tangent line problem. So, let's say you have a function that's a bad looking one. You don't want to use that. Let's say you have a function. X and Y axis. This is F. Okay? Here's the tangent line problem. The tangent line problem says, okay, we know slopes of a line, but can we find the slope of a tangent line? Now what does that mean? Well, the slope of the tangent line is if we get one point and we draw a line through that point. We draw a line that touches just that one point. It's kind of difficult to draw after you kind of look. Okay, I might have to draw it a little bit better. It basically looks like that. A tangent line that only touches that point. That's what a tangent line looks like. That's the only reason why you're in geometry at that point. You know, tangent lines from geometry. But that's the only thing you gotta know. So basically, put it down. We already know that. So tangent line, a line that touches one point of a function. Or just barely grazes it. But yeah, it touches one point of a function on an interval. secant line. How do we get the slope of that? Now, why do we? But the question is not the slope. It really is. Why? How do we? What line? What kind of line? Not what kind. Like, how do we figure out the equation of the tangent line? Well, we need. So what are the forms of the line? Okay, let's just reset everything I'm saying right now. I'm going all over the place. We have a line. It has to be tangent to a point on a curve. How do we find the equation of that line? Well, we know that the equation of a general line is y equals mx plus b. That's the slope-intercept form. But there's another form that's kind of helpful. This one's point slope form. We're going to use this form, because it requires two things: the slope and a point. Well, based on this diagram, we already got one piece of that information, the point. We know the point, and we'll just call it x, comma, f of x. Let's call it. So I know the point, it's x, comma, f of x. There you go, we got it. We just need the slope. That's why the question boils down to, what's the slope? Well, is there another line that we can find the slope in that is closer to the tangent line, but not really a tangent line? The one that we can figure out easily. That's called the secant line. So imagine there's another point right here on my graph. And if we can draw a line through both of those points. There you go, that's the best. That's the secant line. I'll say T for tangent, S for secant. The secant line goes through 2 points of a function. If you remember in geometry, you learned about circles. Your secant line goes through 2 points of the circle, but your tangent line goes through 1. That's where this comes from. Okay, so what's the point? Well, we're going to do some interesting stuff here. What would be an x value here? Well, I just took the x value here and added a number, so I made it bigger. So, because the x value of this point that's further than this x value is just this x value plus some number, because it's more further along. So it's x plus some change in x. This right here, this difference is delta x. What's the slope of the secant line? And before I mention this one, well, if that's the coordinate x plus delta x, x plus some delta x, so that's plus delta x. That's where that comes from. It's just plus some delta x. That's well, then the y coordinate is f of x plus delta x. Okay. Well, what's the slope? Well, remember, slope is the change in y over the change in x. Rise over x. Okay, what's the change in x? It's just right there. It's just change in x. What's the change in y though? This one here. Was the y coordinate of the further point minus it's y2 minus y1, remember? y2 minus y1. y2 minus y1. So we can write the slope of the secant line. I'm going to abbreviate secant with SAC. Slope of the secant line is the change in y over the change in x. Now if I do x2 minus x1, it's just delta x. Sorry for the bad handwriting. That's why I put delta x instead of all the weird stuff here. Okay. Sorry. So that's the slope of the secant line. Now there's one thing we can do. How do we make the secant line? How can we make the slope more accurate, more closer to the tangent line? Let's think about that one real quick. How can we make the slope more accurate to the tangent line? More closer. Well, we can move the point closer. Now if we do it, we get a more accurate slope, right? And now our delta x, hold up, I just ruined my page. Okay, but how do I make it more accurate? Well, we have a tangent line, right? We have the secant line. We can make it more accurate by moving this point more closer. Now we have this secant line. So this is the tangent line, right? And if we even want to, we could make it even more closer. Even more closer. There's a lot of lines, but here's what we're trying to represent. I have a tangent line. I have a secant line. Versus I have a tangent line. Right? If I move this point really, really close, well, my secant line will look really, really close to my tangent line. In fact, it almost looks like it already. And I'm going to use my marker, for example. So sorry, that's supposed to touch the graph, but if I have a point then my secant line, I really wish I had a ruler now. Okay, so I'll just do one short enough to get a marker in it. That's good enough. So if we have okay, so that's a tangent line. But if I have a secant line, and I make this point right here, get really, really close this point, the second point, if I move that point closer, if I move that point closer and closer, then I get more accurate with the slope of my tangent line. So if I move this point closer and closer and closer, this point closer and closer and closer to that point, if I draw a secant line, it gets really, really close to my tangent line. Gotta use a rule for this one. I got to. I want to see if the pencil would work. Okay, I have my tangent line with secant line, and my point gets really, really close. This point right here gets closer. Then my secant line gets really, really close to my tangent line. If my point gets extremely close to the point of tangency, then it's going to get really, really, really close to the tangent line. In fact, it's going to start looking like it. And what happens is the change in y, if we put this point here, our change in our delta x decreases, gets small. So this is the big point. This is the tangent point. And if we get really, really close, then delta x, this delta x value gets closer and closer and closer and closer to just nothing. It gets closer, it approaches 0. And if we draw the secant line every single time and let delta x, the change between these two points, get really, really close to 0, we're going to get a good approximation. And in fact, an exact answer of how to get the tangent line. So the slope of the tangent line would be this. It would be the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. And that is it. Boom. That's the slope of the tangent. And because we know the slope and we know the point, we can find the equation of the tangent line. Ooh, there he goes. Now this thing has a special name. 2 special names, but I'll just give away the first one. This one, I'll erase everything, and then I'll show you the special name. We have so this slope of the tangent line has a special name. F prime of x. Looks like a f prime of x. That is a special name. Okay. The special name. F prime. I'll give away the special name next time. Okay. Let's do some problems with this. Let's use our good old buddy, x squared. And I want to find, this is point 1, 1, and I want to find the equation of the tangent line. I messed up real bad. I want to find the equation of the tangent line at this point, 1, 1, of f of x equals x squared. I want to know how to do it. Find the equation of the tangent line of this function at that point, x squared. How do you do it? Let's plug it in the formula. F prime of x equals, okay. What is f of x plus delta x? Well, let's plug in that inside of x. So if we plug in that inside of x, if we plug in x plus delta x inside of our function, which is x squared, we're going to put it inside of our x. It's going to be inside of our x, which is going to be just that squared, right? So it's x squared. That inside our function. Put that inside our function. That's what we did. Subtract f of x. Wait, that's x squared over delta x. Now there's something wrong with it. Oh, that's the slope of the secant line. You want the slope of the tangent line. So we want that limit as delta x approaches 0. That's f prime of x. Okay? Wait. We did this kind of stuff in limits. This is not foreign stuff because we did this sort of stuff in limits. Sorry. I kind of tripped over something. Hopefully. Oh boy. Hope that's good. Okay. So, we know how to do this on this kind of stuff. Remember how we had x plus h squared minus x squared over h? But we're just replacing that with delta x. We've already done this before. Well, this is equal to the limit as delta x approaches 0. Wait, we know how to do this. X squared plus 2x delta x plus delta x squared minus x squared over delta x. That's if you just simplify that. Okay. Wait, our x squareds cancel out. And we can factor out the delta x. There you go. We factor out a delta x. We can cancel those delta x out. Now we just got the limit as delta x approaches 0 of 2x plus delta x. Wait a second. We can just plug in 0 now. Everything's okay. We don't get 0 over 0 like we did there. We get 2x. Now, wait, what is that? That's f prime of x. Wait, what? Wait, this is the slope of the tangent line? Huh. Wait. Ooh. It's a function of the slope of all the possible tangent lines for every x value. That's pretty cool. So if we want to get a slope of the tangent line at 1, at x equals 1, we can just plug in 1. So f prime of 1, the slope of the tangent line at 1 is 2. Wait, we know the slope, we know the point. The equation of the tangent line equals y minus y1 equals the slope times x minus x1. That's the equation of the tangent line of this function at that point. It's not so hard. It's pretty cool. Pretty cool. Now if I asked you, what's the slope of this tangent line? Well, what's the slope? Just by looking at it. At 0, 0, what would it be? Just by looking at it. Don't use the formula. Look at it. Well, the slope of a horizontal line is 0. Wait a second. And if we evaluate f prime at 0, we also get 0. Interesting. So if you have a textbook that says, if you have a problem that says this, what is f prime of 1? If this is the point 1, negative 2, and they ask you what's f prime of 1, don't do this. You know what the meaning of this is. It's the slope of the tangent line to that point. Well, the slope is 0 because it makes it horizontal line. So that looks like a less than equals. There you go. Okay. Okay. We'll do one more example. What about the square root of x? What will be the tangent line at 1? What will be the equation of the tangent line to the function f of x equals square root of x at each 1? Plug in the formula. So this is f prime of x. So, we plug in the function x squared plus delta x, x plus delta x into the function, we get the square root of x plus delta x minus our function over delta x. Hey, we've done this problem before. We've done it. In fact, we just multiplied by the conjugate. Hopefully you can see that. Okay, what happens here is we get a limit as delta x approaches 0 of x plus delta x. Ooh, minus x over delta x times the square root of x plus delta x plus the square root of x. Oof. Oof, cancel out. Now this is the only term that cancels out with that. So now the limit as delta x approaches 0 of this thing right here. Now we just put in 0. Well, if I put in 0, we get this. And this is just 2 times the square root of x. Okay. That means f prime of x equals 1 over the square root of 1 over 2 root x. That is a derivative. Whoa. I let the cat out of the bag.